All right, great. Okay, well, welcome everyone. Welcome to lecture 2. Hopefully we'll have a little bit better luck today with the technology. We apologize for last time. We're scrambling to get all of our settings figured out, and we thought we had it figured out in WebEx, but a couple things changed last minute. That's kind of how things go sometimes. And yeah, so here we are on Zoom. Hopefully that works for everyone on your end. I think this will be a little bit of a simpler experience. And just a couple of notes on Zoom real quick. So there's a couple less options than in WebEx, but I think that's fine. We'll be doing a little bit of Q&A during the class. We'll ask questions, and when you answer the question, feel free just to respond to all. So you can respond, you can chat to everyone in the chat window. We'll try that today. I think that'll work okay. And then we'll do a couple of Zoom polls today. We'll have a couple multiple choice questions to kind of gauge how you guys are doing. And we'll do those with Zoom polls. Other than that, Zoom should be pretty straightforward. I understand that we had a screen sharing problem last time too. I was only, my main screen is only part of the overall display. I wish I had been able to fix that at the time, but unfortunately I couldn't. So, but today we should have a much better screen sharing experience. I've also set up my phone down here. If I'm looking down there, I'm looking at the same view on my phone that you are to make sure that what you see makes sense. So hopefully technology will go a little bit better today. Arvind and Rohan, anything else to add about Zoom?
No, Professor.
Okay, great. Just wanted to make sure I covered my bases. Okay, great. All right. Okay, well, let's get into it then. So I'll pull up a screen share in just 1 minute. Before I do that, I wanted to go ahead and give Arvind and Rohan a chance to talk about forming groups. So one of the things we'll be doing pretty early in the class is getting you guys into project groups. So there's a little bit of a process we've set up to do that. Arvind and Rohan, do you guys want to share screen for this part, or would you like me to share a screen for this part? Either way is fine with me.
I'll share the screen, Professor.
Okay, great. So I'll hand it over. And yeah, Arvind and Rohan will tell you a little bit about how we're going to be forming project groups.
Yeah, you're able to see my screen, right?
Yes.
Sounds good. Hello, everyone. So today I want to talk about something about the project, the term project, how the teams would be formed, and the stages that you will be going through. So there are some companies, there are some applications of computer vision, something like this, where actually a computer vision algorithm can actually identify what object is this, and in this particular project actually it can identify what sponsor it is. So there are multiple computer vision applications in the world. If you could see this PPT here, there are different types of companies offering different kinds of computer vision applications. Some of them actually worked with the students in this course. You can find the link here, PPT with 40 more interesting companies. So the course project has 4 stages. The first one is the topic selection, and the due date will be 21st of this month. So what you would be doing is you can choose your application, what you wanted to work on from a list of partners we would be providing you on. We'll be announcing soon about the partners and what they would be working on. So you can choose them and you can come up with a proposal, and you can form teams. You can speak with your peers through Piazza. You can discuss, and if there is if there are matches among your ideas, you can form a group. And the deliverable is you have to write a 1-page proposal, and along with your resume of each student. If a team has been formed, it is okay if one of the team members can submit the proposal along with the resumes of all your team members. So we would be opening a assignment on Canvas where you can actually submit these stuff. So ideally, every team member would be having 3 to 4 graduate students and 1 undergraduate student. And we will be making around 16 teams, and every team would be meeting with the professor and a supervising TA. Every team would be assigned a supervising TA. So we'll have several meetings across the semester, and you'll be assigned the credits once the meetings are done at the end of each stage. Yeah, so that's it. Professor, should I go and speak about the other stages as well?
Yeah, maybe just a high level overview. Maybe just spend just another minute or two and just talk about just a high level overview would be perfect. Thanks.
Okay. So in the stage 2, once the teams are decided and you are assigned to your partner, just go through these questions. You have to review 3 academic papers, and you should be able to answer 10 of these questions out of these 3 sections, out of these 4 sections, and check what data you would be working on, and you'll be giving us a deliverable where you need to answer these 10 questions and a Jupyter notebook visualizing your data. And the third stage would be, it's the main part. You build your models, you make experiments, and look at the literature, change the model, train it, and test it, and prepare a very clear Jupyter notebook representing your results. And the final would be demo. Last year we had a poster presentation at Center City campus, but unfortunately because of this pandemic, we shifted it to remote. You would be making a YouTube video where every member would be explaining the part he contributed to the project, and one of the team members would stitch all these videos and send it to us. We'll upload it on YouTube, and you'll upload your code on GitHub as well. There are a few links here available to stitch the videos. And one more important thing we wanted to notice, when you're speaking with your industry partners, please follow up with them and give them regular updates about the status of your project, and loop us as well in the email so that even we'll have a track of what's happening. And here you have a list of all the projects that were done in fall 19 and fall 18. You can go through these, and you can also go through this through this PPT here, just to know what companies and what are the different types of applications the companies are doing outside in the world. That's it.
Great, awesome. Thank you, Arvind. Perfect. Yep. So yeah, that's a great summary, I'd say, of just start thinking about your projects. I know that there's more information to be filled in, and we haven't, had a chance to tell you everything that you can do with computer vision, but it really is time to start thinking about your projects. Who do you want to work with? And I think Arvind made this pretty clear, but just so you guys understand, we're looking to form groups of 4 to 5. Ideally, it's a blend of graduate and undergraduate students. And if you're able to form a group yourself, that's great. But if not, that's fine too. You can hop on Piazza. You can say, hey, I'm interested in working on this. Who else wants to? You can even submit an individual proposal, and we'll use that to assign you to a group. And then finally, one last little thing, we do have to shuffle the groups sometimes. So don't assume that you'll be in the exact group that you request. We may move you around a little bit. We'll only do that to make just to make things even and make sure each group has a good chance of success. So just keep that in mind. So the groups that you submit will be preliminary. And then finally, let me go ahead and share my screen. There's just one more comment I wanted to make. I think Arvind did a great job explaining kind of the different applications, or how to get you started thinking about different applications of computer vision. And let me do a screen share real quick here. And yep, that is coming through. And the GitHub page that we're showing you, just again, just in case you forgot, or all these links are in Canvas, but just so you know. So to get to all these resources, just go to github.com/UNCCV. And then we were just showing you the course project repo. So this is what Arvind was scrolling through, was the main README for the course project repo. And this is just to get you thinking a little bit. We have a few different cool applications of computer vision. Like Arvind said, this deck has a bunch of other companies. Some of these companies have been industry partners for the class in the past. A lot of them haven't, but some of them have. And then there's a few other industry partners that we're looking to add this year. We're probably going to have between 5 and 10 industry partners this year. We had around 10 or 11 last year, but with the pandemic, people are just a little bit busier. So we'll keep you updated on that. The TAs and I are currently talking to different prospective partners. And then the last thing I just want to say is, as you're thinking about topics, there's one little thing, and Arvind talked about it. I just want to highlight it real quick for you. Let me do a quick little zoom in here. Okay, all right, cool. So hopefully you can see this okay. So right here, as you're thinking about what you want to work on, right, there's a million cool things you could do. So these are the criteria. So a good project is it's gonna have to use image or video data as the primary source, because this class is called computer vision, not computer audio or something. You have to leverage some kind of computer vision algorithm on top of your video or image data. And this is a big one. We want you to provide value to someone. We want you to solve a real problem. So a cool computer vision problem that's floating around right now with COVID, there's a few of them, but one cool problem is actually reading people's temperature. So a lot of workplaces now have requirements that employees can't be above a certain temperature. So a bunch of companies right now are actually scrambling to develop solutions that can look at a crowd of people and using a thermal camera plus a regular camera, put those two together to read everyone's temperature. Because you don't want to read temperature of the whole body. You want to read it at this point right here on your temple. Because that gives you the most accurate reading. So to do that, imagine, how do I take an image or a video? How do I find a face? And then how do I find, this part of the face? That's not trivial, right? That's a real computer vision problem that I would say that'd be a kind of a cool project, right? So just think out there, there's a bunch of different cool applications. I encourage you to look at previous years' projects to see what they've done. But this really is a chance. I hope this part's fun because you get to be creative, right? Think of, all the different cool things out there you could do with a camera. There's all kinds of creative ones. And again, I shouldn't even say camera, just images or video, just to point out a couple projects real quick. The first year, we had this interesting project called Yeasty Pie, where they used computer vision to help brew better beer, basically. So they took images of microscopic images of beer, basically, or of yeast, and used a computer vision algorithm to analyze the little yeast molecules in the beer add-in, basically, and use computer vision to figure out the optimal, I think, blend of yeast to use when brewing beer. So that's kind of something you might not think of, right? That was pretty cool. I do think these were graduate students, so they were able to drink. So if you're under 21, you probably could do this, but you can't have any of the beer. So I'm gonna assume everyone's laughing at that joke. I don't know. I'll assume. Another cool one that just, interesting thing, RNA classification. So this group, last year, they figured out how to use computer vision to tell apart different types of molecules from images of RNA molecules to figure out if RNA was going to be, I forgot what the distinction was, but to basically make some kind of biomedical level decisions about these molecules using computer vision, which is pretty cool. And then there's also a bunch of maybe a little bit more standard applications, but all kinds of stuff. This group did some really cool stuff. Let me see if they have a cool, do they have a nice screenshot? Oh, they don't. This group, I wish they had a screenshot. But go look at those projects, chat with your TAs, chat with your friends. Your next job is to start thinking about projects you'd want to be involved in, and try to form a group. And like I said, if you want to submit an individual proposal, that's fine too. But if you do have some folks you want to work with or folks you find on Piazza with similar interest, then it makes it a little easier because you kind of know who you want to work with. So that's that. If you have any questions on projects, feel free to throw them in the chat window now, or otherwise just send us an email. Arvind and Rohan, anything else to add there? I think we covered all our bases for the most part. Anything else to add before we hop into our next item?
I want to add one thing, if the student has any questions, it's better if they could post it on Piazza so that different students can have the same question.
That's a great point. So yeah, I would say that, let me rephrase, great point. Yeah, so if you have a question, post on Piazza. If there's some reason that you don't want it on Piazza, if it's private or something, you can email Arvind or Rohan. But yes, general questions, put them on Piazza. That's a great point. Great, all right. So let's go here now. So let's see here, my screen share is working, great. Okay, so let's go back to our schedule. So here I am back at github.com/UNCCV. And I'm going to go back to our course overview because I just want to look at our schedule. I'm going to go down to our link to our schedule. There we go. Cool. Okay, so today is September 10th. Welcome to lecture number 2. Technology is already going better. I'm pretty sure last lecture we had just figured out how to actually do a screen share at 15 minutes in or 10 minutes in. So today is going better. Thank you for your patience. Okay, cool. So on Zoom now, we got the announcement from the TAs about the project groups. So yeah, I think we're going to get into some real stuff here. You had some required reading, so you all should have looked at this. So this was actually the MIT Summer Project abstract. So for your required reading before today's lecture, you should have had a chance to look at this and read through. this MIT summer project from back in the 1960s. So I think it's pretty interesting. It's pretty cool to see how people 50 years ago were trying to solve similar problems and how maybe they thought things were a little easier than they are. So that was your reading, and that will kind of show up today. But let's go ahead and hop into our first notebook for the day. So here we are. I'm going to make this a bit bigger so we can see a little better. Let's see, maybe there. Okay, we'll try that. Yeah, that looks pretty nice. And actually, this is going to help us right here, I think. No, it's actually the same. Okay, all right, that's fine. Okay, so let me hop to right here. Okay, cool. All right, it's nice to be able to see my own screen. I have my own monitor. Okay, so if you remember, you have a programming challenge to do. It's due in, how long do you have? Let's see, you have like not a ton of time. Definitely, yeah, just a couple weeks. So definitely get started soon. And your programming challenge is to do exactly what this group of researchers did back in the 1950s. Well, they tried to do back in the 60s. They tried to write algorithms to tell apart bricks, balls, and cylinders, which maybe sounds easy, maybe sounds hard, but that's the overall challenge that we're trying to address here. So to get started, we decided to borrow some ideas from this guy named Lawrence Roberts. So he wrote a thesis back in the 50s, actually, about finding the edges, about how to find the edges of images or objects and images. And then we started playing around a little bit. We imported some Python utilities to help us. We imported an image. We talked about the data type of that image. We visualized that image using IMShow. We talked about its shape and its data type, and then we looked at a histogram. And now we're really going to get into some real action here. So we're first just going to do a couple little things to our image to make our problem a little bit more like Robert's problem that he would have solved back in the 50s. And this is common stuff to do anyway, even today. So the first thing we'll do is we're going to scale our image. So we talked about before how the image that we import, it's scaled between 0 and 255, where the brightest values, the white values, have values of 255. And for a number of cases, we're going to want to actually normalize this between 0 and 1. So we want to squish those values down. So doing that is really, really easy. So in Python, we can scale our image just by saying, take this image and divide by 255, and we'll do that. Before I do that, though, actually, real quick, and that's annoying. Okay, what happens there? Oh, yeah, okay, my screen should be coming back, and it's back. Okay, good. All right, so before I do that, real quick, so if you remember, the data type of our image was uint8 before, and Python, let me just ask you guys real quick, who knows if Python is a static or dynamically typed language? Just throw it in the chat window. Is Python statically or dynamically typed? Yes, so Aditya says dynamic, and Hernan agrees, and Christina agrees, and a lot of people agree. All right, good job, everyone, great. So it's dynamic. So in case you don't know, dynamic means that the data type of your objects can change. It's not fixed, right? So in this case, our image array is this unsigned 8-bit integer. Now, when I divide by 255, though, what's going to happen is it's actually Python is going to magically change the data type for us to a float. That allows us to represent decimals, because integers, of course, if you think about the integers between 0 and 1, there's only 2 of them, right? 0 and 1. So that really wouldn't preserve our image very well. So Python will automatically convert to a floating point for us. And here's the same histogram as before. But now in floating point, and it's a scale between 0 and 1, where our very brightest values are 1, and our very darkest black values are 0. Okay, we can still visualize our image. So here's my brick still visualized. I'm going to make this a little smaller so it fits in my zoomed in screen. Let's see, there we go. So there's our scaled image of a brick. It still looks the same, pretty exciting. And now let's do one more thing here. And we're going to convert this to grayscale. And let's spend just a little bit of time talking about Python. And oh my gosh, I keep hitting Command M instead of Control M. Okay, all right. Oh, and by the way, I'm adding more cells to my Jupyter notebook here. To do that, you can go up to cell and you can do, let's see, there should be, let's see. I never do it this way. Let's see, insert, there we go. You go to insert and insert cell below. What I'm doing is I'm hitting Control MB basically, and that does the same thing. Cool. Okay, so we want to convert this image to grayscale. That's the next thing we're going to do. And the reason we're doing that, it's because this is how so we're using this technique called Roberts cross. And this is how the technique is performed usually on black and white images. But converting to black and white in general is not a bad idea. It makes a lot of your image processing simpler. It's usually a pretty nice thing to do. So we're going to do that here. And let's think, just before I show you how to do it, let's think about it for a second, right? So let me do this again. So I'm going to type im.shape. And remember that the shape of our image, let me scroll down a little bit here. Okay, cool. Okay. So the shape of our image is 256 by 256 by 3. So that third dimension, those three, right? I asked you guys this last time. That contains the color information. So that's the color information. Let me show you one more thing, just real quick, because I think it's worth spending a little bit of time today talking about image processing in Python. We're going to have a review session as well. We'll do a little bit more detail. We'll get that scheduled soon. But let's just spend a little bit more time in Python. So let me do something here. So I'm going to do im colon or open bracket colon, comma 0. Okay. So in the chat window, can someone tell me what does this do? So someone who's used Python or NumPy before, what am I doing by saying im open bracket colon, comma 0? What does that do? So I see 3D array. Yeah, it's indexing. Yep, correct. That's right. So can you be a little more specific, right? What are we indexing here? And actually, let me do something else first before I even do that, right? Let's do this. Let's do, yeah, so slice 0 index. Yep. So let me just do one more thing real quick. If I do im of 0, comma 0, right? What will this do? So let me press Shift Enter. Okay. So this corresponds to like the very upper left pixel, and this is the so the dimensions are the height, the width, and the depth is the color information. So this is saying, hey, please give me the upper left, or excuse me, since this is the height dimension first. Okay, so up and down. This is saying give me the top row, and then this is saying give me the first column, the very beginning column, and this is saying give me the first color channel. This is RGB, so it's the red color channel. If I do this, so if I change this to a colon, does anyone know how many numbers will come back when I run the cell? So when I evaluate this cell, and let me go ahead and get this out of here so it's not distracting. So if I do 0, comma 0, comma colon, yep, I got a bunch of 3s. Great job, guys. Good. Okay. I'm going to press Shift Enter. Okay. And what do those 3 numbers represent? What do those 3 numbers mean? Might take a second to type this response. Yeah, it's the red, green, and blue color values for just 1 pixel because I'm doing the 0th pixel. Just for fun, let me do this. If I do im of 100, comma 100, comma colon, what am I doing now? What am I kind of querying or indexing from the image? Yeah, it's the RGB values at that location 100, 100. So if I look back at my image here, right? So it's a little bit weird. So back in most of the graphing you've seen before, usually you'll have your x-axis going this way, left to right, and you'll have your y-axis going vertical, and you usually do x and then y. So in Python, it's a little bit backwards. So the first dimension is down. You can kind of see this here. It starts at 0, then goes down. And the second dimension is to the right. So that kind of matches, but it's a little bit flipped. So 100, comma 100 is going to be 100 down and then 100 over, right? So you notice that when I did 0, 0, I got kind of a value close to 255, 255, 255. I got a pretty high value. Now I should see something darker. And actually, let me ask you this. Take a second and think. I'm about to run this cell. I'm about to query and say, hey, what is im of, and actually I haven't, let me do this real quick. Okay, cool. So I haven't run this yet. I'm about to run it. So this is going to return 3 values to us, right, for that pixel. And remember that 100, 100 is like about right here. It's like here-ish, right? So which of those 3 values do you think will be biggest? The first value, the second value, or the third value? So take a second. Okay, I see a couple of people voting. Yeah. And for those of you that said the first or the red, right, why do you think that that will be the biggest value when we take this sample of the image? What's the reason? Yeah, the brick is red. Yep, very, very concise there. Someone just said brick red. So yeah, the brick is red, right? Yeah, absolutely. So let's see if we got it right. We'll see. I don't know, but you never know. Yeah, if you look at this, so look, the red value is 161. The blue value, sorry, the green value is 108, and the blue value is 92. So there you go. Okay. Now, so all that discussion aside, so we just talked about indexing a little bit. Actually, I have one more thing to show you real quick. What's going to happen before we move on? you know how to do that? There we go, cool. If you want to do multiple cursors at once, you can hold down, it's either the control or the option key in Mac, or the Apple key actually. You can click on two things and I can change them both at once. Here's what I want to do. Now I want to query 500, 500, right? So now I want to see what the value is here. Okay, prediction time. Now that I'm trying to query 500, 500, what is Python going to do? Predictions. Yeah, it's going to error, right? And why will it error? What's the reason? Out of bounds. And is that why is it out of bounds? Because because the image size, right? The image is only 255 by 255, right? Yes, 100%. Cool. So let's run it. And Python complains, right? Cool. Okay. So hopefully that all makes sense. So now let's get to our next item. So the next thing I want us to think about here, right, is how do we convert our image to grayscale, right? How do we do it, right? Before you answer, and I'm going to ask you to think about it in a second, let me ask you this. So this is the shape of our color image, 256 by 256 by 3, right? What will the dimension be of our grayscale image? So throw it in the chat window. What will be the dimension of our grayscale image? I see some ones, kind of. Yeah, there it is. So yes, perfect. So I see a few folks, Sean, Vanessa, yeah, cool. So 255 by 255 by 1. That's right. That's what our answer should be. Okay, cool. So my next question to you then is, how do we do it? What kind of math do we use to, what mathematical operation should we do? Yeah, so I see Abhijit says average all layers. Good, yeah. Does anyone know the name of the function in NumPy to take an average? It's not called average, it's called mean. Yep, good job, np.mean, good. So great, so we have NumPy imported. So I'm gonna do np.mean. And because of the way I imported NumPy, I can also just do mean. But I'll do np.mean because that's going to keep it a little bit more clear. So np.mean is going to take the average. It can take the average of a bunch of stuff. Like if I do this, if I do like 1, 2, 3, right? It's going to say, oh, the average is 2. So that's pretty exciting. For us, we have a multiple dimensional array. So let me show you something, right? So if I just do this, like what if I just did this? What if I just said, hey, give me the mean of the image, right? So what has NumPy done? What is this 194? What has it done for us? Yeah, it's the mean of all the values, right? Has it given us back a grayscale image? No, it's just giving us a number, right? Just one number, right? Okay, cool. So what do we have to change with our numpy.mean function call to make it give us a grayscale image instead of just a number? Any ideas? Axis equals 1. Good, and that's exactly right. Good. So let me show you a little trick from Python, Jupyter kind of stuff. So we're still going to use the mean function, but we're going to use it with an argument. We're going to pass in an additional parameter. So like we have this thing called np.mean, but how do I know what I can pass into it, right? It seems like I can pass in like numbers and like arrays and stuff, and that's cool. But how do I know what else I can pass in? So let me show you something. So what you can do is if you're inside of Jupyter, you can press Shift-Tab, and it will actually bring up a little dialog box, right? So to get to this, again, I put my cursor inside of here and I press Shift-Tab, and I got a nice little dialog box. And it gives you some of the typical arguments, which is helpful. You can also press the plus sign, and it will give you a little bit of documentation. It'll give you the doc string for this method. And here we go. So if we read the documentation, it says, okay, you can tell me about this parameter called axis. It's optional, you don't have to have it. And it's the axis or axes along which the means are computed. So what this is saying is that if you give me a multi-dimensional array, and our image is it's a 3-dimensional array, multi-dimensional, you can ask NumPy to just take the mean across one dimension, across one of your 3 dimensions or however many dimensions you have. So that's what we're going to do. So let's try it. So what we're going to do then is we're going to hand in IM, and let me try something real quick. So I'm going to do axis, but I'm going to do the wrong thing. I'm going to say axis equals 0. Now, before I run this, let me actually do something. I'm trying to compute a grayscale image, so I'm gonna pass this back into a variable called im_gray, and I'm gonna go ahead and do this im_gray.shape so we can see what shape we end up with. And I'm kind of doing the wrong thing, so I'm saying axis equals 0. So the 0 axis, think about this for a second. So remember, Python is 0 indexed, so you don't start at 1, you start at 0. So remember, in images, the 0th index, the first index, corresponds to up and down. the first index, index 1, corresponds to left and right, and the third index for images corresponds to color. So take a second and think to yourself, what dimension will I get out when I run this code? I'm taking the average. It's kind of the wrong thing. I'm taking the average across the 0th dimension. So throw in the chat window, what will be when I run, let me actually comment this out real quick. Let's see, can I do that? There. No? Why can't I do that? No. That's annoying. Okay, keep thinking while I'm fighting with trying to comment this out. There we go. Cool. All right. Okay, yes. So when I run these two cells, what is the output going to be? So yeah, so I see a 1 by 255 by 3. I like that. It's either going to be that or it's just going to be 255 by 3 because this is going to take the average vertically. It's going to smush all the columns into like one row basically. So let's try it. Let's run this. Let's run this. And there you go. It actually loses that first dimension because if it's a 1, it can just kind of throw that away. But yeah, it's 256 by 3. So this is still not the right shape. Remember, we decided it should be 255 by 255 to be a grayscale image. So let me ask you this then. What should I change? So I've done the wrong thing here. What should I change to be able to take to compute a grayscale image instead of just computing this row? Yeah, axis equals 2. That's right. So I'm going to change this to axis equals 2. Now that shape makes a lot of sense. And now to really see if we figured it out, I'm going to do IAMShow of IAMGray, and we're going to get something like this. Now this might look a little confusing, and I want to talk about it. Let me make it a little bit bigger. And there may be something surprising about this image when you look at it that maybe you didn't expect this. What maybe looks a little bit surprising about this grayscale image that you might not have expected? What might look a little weird? Yeah, it's the color, right? Yeah, it's got this color, right? Okay, cool. Does anyone know why? Why is Python deciding to, or really why is Matplotlib and IAMShow trying to do this color thing? Does anyone know why? Like what's going on? Okay, I got some good guesses. Kind of. I haven't quite seen what I'm looking for yet. We don't have 3 colors. It's truly, it's kind of a grayscale. It's a one colored channel image. So let me show you something. I'm going to add one more piece of information that I think will help. I'm going to type color bar like this, and let's see what happens. Okay, this might start to shed a little bit of light. So I added this color bar thing, and notice that this color bar thing has popped up. Okay, and someone's asking if the lecture is being recorded. It is, and we will post this later in the week. So yeah, don't worry about writing everything down. Oh, and I should have said this first as well. So yeah, these are all being recorded. They will be posted. So please don't worry about having to write everything down that I do. Feel free to take notes if you would like, but you certainly don't have to. And don't let trying to capture everything distract from just being in the moment and trying to follow along. Yeah, so what's happening here is Matplotlib by default uses what's called the Viridis color map. And what that does is it maps every value to a color. And using a color map like this, it's actually a little bit easier, and sometimes we'll use this later in the course. It's easier to see details, basically. But so let me show you something real quick. So when I do IAMShow, again, there's another argument I can pass in. So you see that second argument is called CMap. So CMap is for color map. So what I can do is I can pass in different color maps, and you can go look at the documentation to see a list of all the different color maps. But I know that the one that we're using right now is called Viridis. So if I run this, like nothing should happen. It should be the same. Yeah, okay, cool. So it's the same. That was the default. But now if I change this to gray, and I can never remember if it's capital or lowercase g, but let's just try it. Yeah, there we go, cool. So this maybe looks more like what you expected. So the reason it didn't show up the way you thought, it's not because there was still color information. It's because Matplotlib uses a color map to try to make it easier to see stuff in images. And the default color map in Matplotlib is that Viridis color map and not a grayscale color map. So now it looks like a grayscale image. So hopefully that makes sense. That's how we compute and visualize a grayscale image from a color image. If you have any questions on that, throw them in the chat box. I'll keep talking about how we put that into a function now. And we spent maybe a little more time on that than we would, but I think it's good to spend a little time at the beginning. And on the original plan for today, I had some time on Jupyter and image processing. So I think it's good we spend a little bit of time on that. So here, I've wrapped up this method that we just learned in p.mean axis equals 2. I've wrapped it up into a method, convert to grayscale. It's a very short one-line method. It has a little doc string here that explains how it works. It's nice to use doc strings, don't always have to do it. So let's see here. So, and actually a little question, can't we just change it on and get the same result before doing ABG? I don't quite follow your question, Si. Maybe ask it again and the TAs can help sort it out. I don't quite follow the question though. It seems like a good question. I'll keep going, and then Arvin and Rohan, if there's a good question you see come through, or if Si is able to clarify his question, then let's talk about it. But it seems like a good question. I can't quite follow it. Okay, so here's our method, our convert to grayscale method. So I just wrap this up inside in Python to make a method. You use this thing called def, and then you can pass in images into your method to get an output. So we've done that here, and we get out, again, a grayscale brick, and I'm using this grayscale color map. Great. All right, cool. So we've made that far. Now let's get into kind of the real meat of the lecture. So in Robert's original paper, he did some math. So again, computer vision at the end of the day, there's a lot of code, but there's also, you know, a lot of this really comes from math. That's kind of where a lot of this stuff starts. And definitely a goal that I have for you in the course is to become more comfortable with going back and forth between math and code, because that will be a really valuable skill for you. Whether or not you go into academia or industry or whatever you do, it's nice to have some mathematical backing to what you're doing. So here's the equations from Robert's original paper. The first thing that he did, which is kind of interesting, is he took the square root. So he said, okay, if you want to find edges in an image, first take the square root of all your pixel values. And let's just talk about his notation here a little bit. So he has this x and then little I comma little j. What is this little I comma little j? What is he trying to tell us to do? Like, what is the purpose of having this little I and j in the formula? Does anyone know? Yeah, it's an index, right? So yeah, what he's saying is that he's saying do this for every pixel is what he's really saying. So he's saying, okay, for every pixel in the image, just take its square root. It turns out that actually modern cameras, like the one I'm talking to you on, they use something called gamma correction. And this is not a big deal for the course, but it's kind of cool to know. They use something called gamma correction. So whenever an image is taken on a camera like this, or really any modern camera, the square root is already taken. And it kind of has to do with how our eyes perceive color intensity. If you're interested, there's a really good video from Minute Physics you can check out. But basically, we're going to skip this first step. So Roberts, in his original paper, said, hey, take the square root first. His camera didn't do this because it was 1955 or something crazy. But the next step we are going to take very seriously, and this is really how he's having us find edges. So I want to take, 10 minutes, 5 minutes, 10 minutes, and really let's try to understand this equation. Let's really dig into it. So here's the equation, and I think I have it written down again below. Yeah, here it is. So I really want to take a minute and I want you guys to think about what this equation says to do. So I just made it a little bigger. So here's the big bad equation. Hope it doesn't look too scary. And y is our image. It's after we take the square root, but we're skipping that square root step. And I want you to think for a second, why did this guy, Roberts, why did he decide that doing this little piece of math that I'm showing you, why is this a good idea? How is this going to help us find edges? So as you're looking at this equation, and I say a good question, is it similar to convolution? Kind of, a little bit. It's kind of, in a way, it's a good point. And it should remind you of distance maybe too, right? It looks maybe like some distance formulas. So start thinking about it a little bit and specifically pay attention to these indices, right? So I've got y of I comma j, right? And I've got I plus 1, and I've got j plus 1, right? And here I've got y of I plus 1 comma j minus y of I comma j plus 1. So just think for a second, what is this doing exactly? And we'll get into some answers in a second here, but we might try. Yeah, so this is where I normally draw on the whiteboard, and I might draw on a tablet here. We'll see. I'm trying to decide if we want to or not. So yeah, let's try it. Let's give it a shot here. So we'll try it. We'll see how it goes. So let me switch my screen share for a second. And actually, what I really want to do, so start thinking about this equation. While you do that, we're going to try this. Let's see how it goes. That's cool. All right, so keep thinking about what this equation does exactly. And while you're doing that, just give me 1 second. Cool. All right. Ah, beautiful. Cool. Okay, so I'm going to switch my screen share real quick. Share, and we do application window. Ooh, that's annoying. Okay, 1 second. Okay, this has to apparently be on the same desktop. Okay, all right, good. Now let's try share screen. Application window, yes, perfect. Okay, so now, yes, now I can do some drawing, I think. Okay, let me do this a little bit. Okay, so I copied over our equation. Let me try this real quick. Okay, that's only picking up part of the screen. Now I should get my scaling about right. Okay, well, that's annoying. It still only takes up part of the screen. Okay. That's a little better. Okay, all right, let's try this. So here's my equation again, right here. And what I want to start thinking about is this really pertains just to one little patch of pixels is what it really pertains to. That's what we're really talking about here. So what I want us to think about is imagine that the whole background is like one big image. And we're just thinking about how a little set of little patch, we're doing this operation on a little patch of the image. So let me draw that now real quick. So we've got this whole big image, and we just want to think about, let's just think about a few pixels real quick. So we've got this 1 pixel. Let's say we've got a little grid of pixels that we're considering, a 2 by 2 grid. And let's say that this is y of I comma j. So this is I comma j right here. Okay, cool. All right. And that's so weird. The screen share is cutting off. I'm so glad that I'm joining the meeting and looking at the same screen you guys are, because it's cut off the edge. I can see it, but you can't. But now you should be able to see the whole thing. Yeah, okay. So this is I comma j. Now in the chat box, for a second, so where is this pixel? I plus 1, j plus 1. Remember overall, let me just draw one more little thing on here. Remember that the I direction is this way. So I goes down. And the j direction is this way because our first index, that's a longer line than I wanted. Oh God, that's terrible. Okay, let's try this. Okay, this is when I missed the whiteboard. All right, there we go. Cool. All right, so yeah, so maybe some of you put it in the chat window already. Where is I plus 1, j plus 1? Bottom right, yep, a lot of you have it right. Fantastic. So this down here, this is the I plus 1, j plus 1. Cool. Okay, let's keep going. So this one, so I plus 1 comma j, where is that going to be? What location? So I see some top rights and I see some bottom lefts. So some of you are right, some of you are wrong, no problem. Remember that I comes first and I is up and down, right? So if we go, this is saying move 1 step in the I direction, and in computer vision, or at least in Python, the first axis, the I dimension is down positive. So we're going to go down. So I plus 1 is right here. I plus 1 is right here. And then this is still just the jth column. Okay. And then finally, you probably guessed this already. This is I comma j plus 1 right here. Okay. So now let's think about Robert's cross for a second, right? So what is he asking us to do? So he's saying for a little patch of pixels, he's saying take this value up here in the upper left-hand corner and subtract that value. So he's saying take this and take that away, basically, right? So it's kind of like a subtraction, right? So subtract this, right? Do a subtraction here. And then he's saying also do the same thing. So take this value and subtract this value, right? And then he's saying square them and add them all together, and then take the square root. That's what he's saying. Okay. So start thinking for a second, right? Why is he having us do this, right? And then the overall idea is here, can we find edges, right? Why is he having us do this? So let me hop back. Let me change my screen share here, back to the Jupyter Notebook, and let's move forward here. And hopefully this has got you thinking a little bit. Okay, cool. So here's a fancier drawing of it, right? So we've got this little patch that's moving through our image, and that maybe wasn't clear at the beginning. The idea here is that he's saying, okay, just consider little patches of 2 by 2 for a little while. And then for those 2 by 2 patches, we're going to do this local operation. We're going to compute some value, and then we're going to have some output. So that's what he's really saying. And the thing I want to start thinking about now is, what will this respond to? Yeah, exactly. Okay, cool. So we're going to do this little difference operator, right? And I want to start thinking about, okay, what kinds of little patches are going to make for a large value of z? So think about little regions of the image, little 2x2 grids, right? What kinds of pixel values are going to lead to large values of z, which would be a large value of Roberts cross? So I've put this here for you in a nice multiple choice question, and this will be a poll. So this will be our first poll. So Arvin and Rohan will set this up in a second. But start thinking here, right? And I've given you 4 examples. I've said, okay, here's an example with, all gray 0.5 values. Here's an example with 0.5s and white values of 1. Here's an example of 0s and 1s. So just take a minute, right? And don't put your answer in the chat. We'll put it in the poll in a second, okay? So take a minute, and when you're ready, put it in the poll. I have to change my camera battery real quick. There's a part I'm waiting down to come in the mail, and my camera battery is going to die. So I'm going to go away for like 1 minute. And when I come back, we'll look at the poll results. So take a minute, think through this question. Which patch would give us the biggest value of Roberts cross? I'll be back in 1 minute. Okay, everyone, can you guys still hear me okay, Rohan and Arvin?
Yes, Professor.
Okay, excellent, great. All right. Okay, so I see the poll results. Wow, you guys are doing really well. Okay, I need to go a little faster, I guess, or be more confusing. Okay, so yeah, you guys did a really good job. So 96% of you said C. Yeah, that's great. So I think the intuition here, then hopefully this is kind of coming into focus for you guys a little bit, is that if you zoom way in on an image, right? Imagine that brick image and you zoom way in, the edges should look kind of like this, right? You should have a very dark value next to a very light value. That's kind of what edges are, right? They're a difference in contrast, or they're a large value of contrast. So Roberts cross is going to be maximized in cases like this, where you have big edges, right? So that's why he developed it, right? He was thinking, okay, what math can I do to find edges? And this will respond very strongly to edge patches like that. So let's keep moving here for a second. And actually, yeah, I think I might have just shown you the answer. That's a great question. Why the cross? Yeah, we'll see another edge detector in a minute that doesn't quite use a cross. It's a good question, right? And actually, there's some kind of holes and problems with Roberts cross, which we'll get into in a minute. And yeah, good question. That's a really great question, actually. Does it work only for vertical edges? I'm actually about to ask you that, right? But before I do, I have 2 more questions for you to think about for a second. The first question is what kind of patch value would minimize Roberts cross, right? We talked about a kind of patch that would maximize it. So just take a second. You can throw it in the chat window. What kind of patch would minimize, make it really flat? Yeah, a lot of people say A, exactly right. So it's any case where you have like a very smooth, flat value, right? And let me close the poll here so I can see my screen. Yep, cool. So yeah, and if it was all 1s, for example, that would also, it should, anywhere where there's no edges, there's no detail, right? Cool. So the next question I have for you, so I showed you, hey, this type of patch will maximize the value of Roberts cross. Oh, and I see a couple questions. Would D, right? So would D also minimize Roberts cross? So I think it does, which is kind of funny. It's kind of one of those things like, because this kind of could be an edge, right? This is kind of a problem with Roberts cross. In theory, you would like it only to be minimum with like this, but yeah, this would also minimize it, right? Because let's look at the formula, right? So you have 0 minus 0, squared is 0 plus 1 minus 1. Yeah, so this would also minimize it. And that maybe isn't quite how it should work. So in the next lecture, we're going to cover a better edge detector called the Sobel edge detector. But it's worth thinking about the problems with Robert's cross because it'll really help you understand what makes a good filter, what makes a good edge detector. Okay, one more question for you then. So that's a great question about D. You're right, D also minimizes Robert's cross. One other question for you though. So I showed you that, hey, C, gives us a really maximum value. I think it gives us the value of the square root of 2, 1.414. Are there other patches besides C that are not shown here that we could also make up that would also maximize Robert's cross? So just take a second and see if you can think of other patches that would also maximize Robert's cross. And what I'd like you to think for a second is how many of those patches exist, right? So think of another patch, right? And how many other patches would give you exactly the square root of 2 for Robert's cross? So I see an inverted C. Yeah. Yeah, it's all the permutations of C, right? So here they are. So here are 4 other patches that would all maximize Robert's cross. And those look like edges, right? Edges are where we have a dark region to a light region. So the cross captures that pretty well. What the cross doesn't capture though is this case very well, right? But the cross does capture these well, so that's great. So it should work reasonably well. Okay, so I've shown you the math. Now I'm going to show you the code, and I think we have about 25 minutes left, I think. Let's look at the code together here now. So how do we code this up in Python, right? Actually, before I show you the code, sorry, there's one more thing I want to show you. I would like to show you just a little animation to kind of give you a sense for what's going on here. So let me talk you through this little animation I made to demonstrate Robert's cross. So here is the original image over here, and we're about to code this up, so you'll see the actual code. So we're taking our little 2x2 kernel, right, and we're moving it down the image one column at a time, basically. And for every kernel, we're processing Robert's cross, and we're taking the value of Robert's cross and we're putting it over here in this new image we call edges. It's like the edge image. And over here, we're actually using that Viridis color map. So really high values are going to be yellow, really low values are going to be purple. And you can see here, I'm showing you 2 other things. So I put a little blue box around the green box. And the blue box contains, it's just a little bit of a bigger window so you can really see. But the green box, that's where Robert's cross is being computed. And as I move my kernel, my little box up and down or down, you can see the pixel intensity values change. And I'm going to pause it on an edge. Like here's a really nice edge, right? So this part has lower pixel values. The height here is the pixel intensity value. And when we hit that edge, we have nice low values. Half of Robert's cross, right? It'll come in 1 second. Here we go. Get ready there. So you got nice low values, nice high values. So you get a high value of Robert's cross, and you start to see this edge coming in the computed edge image. So that hopefully gives you a little bit of sense for how Robert's cross works. And now that you maybe understand the math and a little bit of the intuition, let's make it happen in code, right? So that's the big theme in this class, I would say, is trying to bring together your math, your intuition, and your code, right? So hopefully this visualization gives you a little bit more intuition, and we talked through some examples to give you more intuition. We looked at the math, and now we're going to look at the code. So let's do it. And as we get into it here, one thing that's going to be really important for us to figure out is how many individual patches do we need to do our computation for, right? So we know we want to cover our whole image, and we have to cover these 2x2 patches, right, as we move through our whole image, because that's going to control how big our output is. Does that make sense? So our input image is 256 by 256, but I want to think for a second, how big is our output image, and how many different grids do we have to process? So that's going to be our next question. I think it's going to be multiple choice. I think so. Let's have a look. Yeah, there we go. Okay, our next poll. Good, and there's one assumption though that I want to show you first. So before we open the poll, guys, let me hop back to drawing just for 1 second here. So, because I want to show you there's one assumption that we're going to make, and it's going to be very common in computer vision. It's called the padding of the borders, basically. So yeah, you can see my screen now. Perfect. Okay. So here's the assumption I want to just talk you through briefly. So we've got this whole big image. Oops, that's not what, well, actually I could do it that way. Oh, that'd be fun. Okay. So instead of me freehanding a crappy square, I'm going to use technology. I'm going to try to use technology to make a, oh gosh, what do I do? Hold on. Bear with me. You can tell the drawing portion of this Here's what the learning curve is. Okay, come on. Okay. There we go. Now I think you can see my screen. Okay. So here, let's call this our big image. So here's our big image. And actually, it's kind of bothering me that it's not a square. There's my OCD coming out. So here is there we go. Here's our big image, 255 by 255. And we have this little kernel that we're going to move all over our image. And our little kernel is only, I'm going to draw a new one now, basically. It's only 2 by 2. There we go. Let's make it a different color. All right, cool. So we've got this little kernel. And you've probably guessed we're going to start this kernel in the upper left-hand corner. So like the first little position we'll evaluate. Let me make this a better color that you can see. There we go. So we're going to start this kernel up here. And we're going to move it down our image and process all these different patches, right? And then what you might start thinking to yourself is, okay, when I get to the bottom, right? When I get to the bottom of this image, right? I'm going to go down, 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 down. I get to here, right? Where do I stop? And later when we get to deep learning, we'll talk about padding and striding and all this stuff, and it'll become a little more clear. But for now, you might be like saying, okay, do I actually get to go beyond the image a little bit? And for now, we're going to say no, because there's no pixels to process there. Like, what would you plug in? So now we're going to say we're going to stop right there. Does that make sense? So when we're analyzing this image with Roberts Cross, we're going to start in the very upper left-hand corner and process a little 2 by 2 grid. And we're going to go all the way down, and we're going to stop right here. And we're not going to go beyond the edges. Same thing over here. We're going to go all the way to the edge, and we're going to stop right there. So hopefully that helps you think about how we're going to move this little 2 by 2 kernel across our whole image. So let me go back to the question, and we'll open up the poll here in a second. Let me go to application window, and let's go here, share. Cool. Okay, great. So here's our question then. So based on the assumptions I just told you and an explanation of how Roberts Cross works, to process a 256 by 256 pixel image, I think I might have said 255, sorry, it's 256 by 256. How many times do I need to compute Roberts Cross, right? So please take a minute, put your answer in the poll. How many Roberts Cross calculations do I need to do to process this whole image? Okay, so you've had a minute to think. Hopefully the question makes sense. So let's go ahead and close the poll. Let's see what we get here. Okay, so right, so we're getting more of a spread of answers, which I'm happy about. If everyone got the first question, like everyone got right, which is great. But I think that means that I'm going a little too slowly, right? So if you got it wrong, that's fine. It just means you're thinking. So that's the whole idea. If you got every question right, you wouldn't learn anything in this class, I don't think, right? So hopefully you'll learn something. Okay, right, so let's get into it now. So let me go back to drawing to talk through the answer to this question. So let me switch back, and this has worked okay so far. Let me go back to my drawing. Okay, and you can see this now. Okay, so let's kind of get into it here. And what I'm actually going to do to make life a little bit easier, I like to kind of use simple examples. Let's go simpler here, and let's assume for a second, I know our images that I asked you about, I know that they were 256 by 256. Let's assume for a second that our images are only 8 by 8, right? Just for a second. So let's say this is 8 pixels this way. It's this tiny like 8 pixel image, and this is just 8 pixels this way, basically, right? And let's start to think here for a second about how many times we have to do the math. So here's our first position, right? So we have our first 0, 1, 0, 1 kind of location. And let me copy and paste this. Cool. Okay. So some of you who picked some of the lower answers, you might have assumed that we were going to take a step like this. And I didn't really tell you. I probably should have told you in hindsight, but it's good you thought through it. What you usually do with convolution, actually almost always, unless you change your stride, which we'll get into in deep learning, but for now, we're going to assume we do this. So we're just going to take little steps of 1 because we don't want to miss anything, right? So we're just going to take little steps of 1, basically, right? So here's our first step, our second step, our third step, our fourth step. We're going to keep taking these little steps of 1. I'll keep going here, and I think, and of course my sizes aren't going to be perfect because I didn't actually make this 8 times larger than 1 unit, but I think what you'll start to see here, and maybe this will work. Let's see, how many do I end up with here? It's a little bit off, so let's do this. Okay. All right. So 1, 2, 3, 4, 5, 6, 7. Oh, that was perfect. Yeah, I'm kind of proud of myself. All right, cool. Okay, so that's 8 pixels down, right? Okay, but now how many boxes are there? Ready? So it's 1 box, 2 box, oops, sorry. 1 box, 2 box, 3 box, 4 box, 5 box, 6 box, 7. So you can only fit 7 boxes. Does that make sense? So even though it's an 8 tall image, right, you can only fit 7 because there's like 1 minus because you can't go to the edge, right? So what that means really is you end up with 7 boxes across, right? And you can imagine the same thing up and down. So even though the image is 8 tall and 8 wide, you actually end up with 7. So we end up with 7 here. And you can imagine you'll end up with 7 this way as well. So if you do the same thing this way, you'll end up with 7. So you get this 7 by 7 grid. So the answer for the 8 by 8 case is 7 times 7 is equal to 49. So for the 8 by 8 case, it would be 49 operations. Okay. And now for the 256 by 256 case that I asked you about, let me ask you in the chat. So what 2 numbers should I multiply together for the 256 by 256 case? Yes, 255. It's 1 less, right? We're going to do 1 less. So we do 255 times 255, which I believe is like right around 65,000-ish. Let's go have a look. Let me go back to the lecture notes, which are here. Cool. All right, great. Okay, perfect. Okay, so the answer is C. So a lot of you got it right. Great job. So that's what the answer is. So that makes sense. Great. If not, go back and review the notes. It shouldn't be too bad, and ask on Piazza if there is any confusion. So now we're finally getting to write some code. Okay, and it's 1:30 or it's 3:30. Okay, so yeah. So let's go ahead and go through this implementation. So here is Robert's cross in Python, and the reason I asked you again about the shape is because it's about to matter a lot. And it'd be nice to code this from scratch. Maybe a good thing to test your Python understanding is to try to code this from scratch. But let's go ahead and walk through my implementation here. And I would like to say that I've written this method, this Robert's cross method. I've written it in a way that is going to be very easy to read. It's going to be very pedagogical, kind of clear, but it's also real slow. So as we get later into the class, we'll find more efficient ways of doing these things. But this really is to kind of explain, how this works. So let's walk through it. So this is my Robert's cross method. It takes in X, which is a grayscale image, floating point. And first thing I'm going to do is I'm going to compute an empty array that will hold the answer. I'm not computing the answer yet, but I'm making this image called edges. And notice my shape here, right? So I'm doing how big should I make my edge output? I'm making it the shape of the original image -1. And it's for the exact reason that we just talked about. So an 8 by 8 became a 7 by 7. Same thing here, right? So whatever the input shape is, subtract 1, that's your output shape. Now, can anyone tell me, what am I doing here? So what am I doing with this for loop? I'm iterating across what? Every pixel, kind of. So you're close. Every pixel is close. True, but like, what does it mean? Looping the pixels, kind of just the first for loop. Yeah, okay, we're getting warmer, right? So someone said row, someone said column. Which one is it? Is it rows or columns? What am I doing? Row. It's row. Okay. Why? And why is it row? Why am I iterating over? How do you know? How do you know that I'm iterating over the rows, not the columns? A lot of you are right. Yeah, it's shape of 0. All right. So remember, the 0th index is down, right? So if I'm stepping down, just like that animation. Remember this? I could have done this animation differently, right? I could have gone left to right. You'd actually get the same answer. But I'm kind of following the convention of doing down first. So yeah, I'm going down. So I'm iterating over the rows first. Okay. Then I'm iterating over the columns. So I'm doing rows and then columns for this for loop. And then here, let's take a second to think about this. So what I'm doing here in this little snippet is I'm grabbing a 2 by 2 patch. So if like I is like 100, here I'm going from the 100th location to the 102nd pixel location in the vertical direction. And I'm going from the 100th location to the 102nd location in the horizontal direction if j was 100. So I'm grabbing that patch, and here I'm actually doing Robert's cross. So this should look a lot like that formula, right? So I'm taking the upper left corner of the patch, subtracting the bottom right corner of the patch, I'm squaring it. In Python, square is asterisk, asterisk. I don't know why, but that's how you write squared in Python. And then I'm taking the lower left corner, and then I'm subtracting the upper right corner, and then I'm squaring it. So that's it. So that is Robert's cross in a Python method. So hopefully that makes sense. And to actually use Robert's cross, all I have to do is type edges equals Robert's cross of x, because x is our image. So I'll run that. And now I will run this to visualize it. Hopefully it works. Let's see here. There we go. Cool. All right. So there you go. So there is an image that has been processed by Robert's cross. So Robert's made this algorithm back in the 50s, and here we are using it in 2020. It still works, and it works pretty well. So you can see, which pixels in the image are the brightest. It's the edges, right? You can see the edges are kind of glowing here. You do see some noise, right? So you see all this little noise. We'll talk about that soon and what you can kind of do about that. But the edges are really, really glowing. So we've kind of found the edges, sort of, right? We have an image where we have high values at the edges. So yeah, that's not bad, right? So using this formula, we found the edges in our image. So hopefully that makes sense. And a lot of folks on this programming challenge, I'm not going to tell you how to do the programming challenge at all, but I know a lot of the solutions out there use edges. So as you're thinking about how to do the challenge, maybe start by doing edges. Maybe find the edges and then see what you can do with those. See what a good next step to do with these edges is. So let's get into it here a little bit more. And like I said, this can be a beginning step at finding bricks, balls, and cylinders. But I want to share a couple just quotes from Robert's PhD thesis. So he worked on this for 4 years or whatever, and I think he was probably one of the first people to realize that computer vision's like really hard. Because here's a quote, and this is from his thesis, right? So you can tell he's getting a little overwhelmed. So he says, "It is no simple chore to obtain a list of lines and their endpoints from a 500,000 bit array of data." And that's kind of like the size that we're working with, a big array of data. Oops. So it's no simple chore to do this. And notice that if you could obtain a list of lines, that would help you with this programming challenge, right? You could find the edges of the brick maybe. A simple procedure might be to choose a clip level and start tracing out lines which correspond to a string of adjacent cells in a raster, all of whose values are above some clip level. Okay, so let me talk you through that idea really quick. So what he's saying is that it's basically the idea that we would call thresholding in this class, and we're going to be doing that a lot. When he says clip level, what he's saying is, okay, this image is still kind of continuous, right? There's like small values of edges and big values of edges. It might be nice just to pick out which pixels are either edges or like not edges, like make it binary. Tell me which pixels are edges, which pixels are not edges. So we can do that by thresholding, which we'll do soon. So all you do is you say, okay, give me the pixel values that are greater than, let's say, 0.4 or something, and you'll just get back, those values. So he's saying that you could do that, but what he says here is that he says the hopelessness of this procedure is easily seen when one looks at typical pictures and considers them as a three-dimensional surface where the z values are used as the height. So he's saying you'll realize that this might work okay for and if you think about our programming challenge, the thresholding thing will work really well for the easy images. And again, if you get the easy images right and some of the medium, you'll get a really good score. So you don't have to get the hard images. But I'll show you in a second when we get to the hard images. Just trying to threshold the edges is it's like impossible. So let me show you. So Robert says, the hopelessness of this procedure is easily seen when one looks at typical pictures and considers them as a three-dimensional surface where the z values are used as height. Let me show you real quick. So here is one of these edge images, and I'm plotting the value of Robert's cross. I'm plotting it as the height, right? So you see all these spikes around it. And that looks not too bad, right? We kind of have like a nice fence around the image. You could write some algorithm that could maybe pull out those edges. But now let's look at this for a harder image, right? So here is the picture of the ball on the book, right? And Robert's cross, it finds the edges of the ball, but it also finds like everywhere on the book that has any kind of contrast, it's just so noisy, right? There's the ball on the book, right? And yeah, when we look at it as a three-dimensional height thing, it's just like crazy, right? And hopefully that gives you a sense for, why computer vision can be difficult. And you'll experience this firsthand as you go through the programming challenge. So we've got just a few minutes left, but I just want to emphasize just some kind of like, I don't know, philosophy of computer vision. It's helpful as you're thinking about what kind of discipline computer vision is. It'll help you through this class, and it might help you think about if you're considering a career in machine learning or computer vision, this might help you think about how this would compare to other careers. So here's a good quote from Robert. So he says, "The procedure I have developed for finding the lines from differential pictures," a differential picture is what he called the edge image. He called it a differential picture, "makes mistakes in complex pictures and is a complex special purpose program demonstrating very few general concepts." So he's, again, in his PhD thesis, he's kind of saying like, yeah, I kind of solved this problem, but this is not like a general, applicable problem that's going to solve a bunch of other computer vision problems. And this is a really big theme that you're going to see again and again in computer vision. So if you have an undergraduate degree or you've studied physics or mathematics or some of the older sciences, there's going to be a big difference between those kinds of science classes and computer vision. So like in Newtonian physics, like, in high school physics or whenever you took physics, they can tell you like these unifying principles. They can say, hey, F equals ma, and we know it for these reasons, right? Or at least under these conditions, F equals ma, or whatever the unifying principles are. In computer vision, we really don't have anything like that. I can't just sit here and tell you this is the algorithm to solve that. We're getting there. We're getting better, but computer vision is only 50 years old, 50 or 60 years old. And physics is a lot older, right? So modern physics, you could say 1750s, maybe something like that. Newton, maybe a little older, but it's had 300 years to mature. Mathematics is millennia old, right? A couple thousand years. It's had a long time to mature. Chemistry, hundreds of years old. Computer vision is not. So either that might turn you off a little bit because what it means is that there's going to be more experimentation, more trial and error. To me, I think it's really exciting because it means that all the cool stuff hasn't been figured out yet, right? So maybe you'll figure out some of the cool stuff because there's a bunch of open questions. No one has found the underlying principles. Maybe deep learning is part of it, we'll see, but there's a bunch of mysteries, right? We just don't know, it's a new field. So keep that in mind in this class. If it feels like there's no one unique answer, it's because there's not. There's definitely not in computer vision. Okay. So just to finish up here, what I'd like you to do over the weekend, basically. So you have some reading to do. You're going to watch a video about the Sobel Edge Finder. You're going to watch maybe a filtering video. That's pretty easy. What I'd really like you to do is just start thinking about how would you make Roberts Cross better, maybe before you even watch the video, right? And you're going to be starting your programming challenge. I encourage you to start this weekend, especially if you're considering if you want to stay in the class or not. Then the programming challenge should give you a sense for really what you're up against. Again, be persistent, don't give up, hang in there. But for some students, if they really haven't had a lot of Python experience, it's more helpful to figure out quickly whether or not this is the right class for you. And if you go spend 10 hours on the programming challenge and you've made zero progress, even though you've been on Piazza and you've asked a bunch of people, then you might want to consider if you're on the fence with dropping or not. If you really want to be in here, then stay in here, keep fighting. I applaud you, but hopefully that first programming challenge will help give you a sense for what the difficulty of the class will be. So the last thing I'll say, just before we wrap up, we've got 2 minutes here, is I want you to think about how can you make Roberts Cross better, right? And I point out in the notebook, come look at the notebook later, right? But I point out some problems. So we know that it's noisy. You'll get all this noise and stuff when you do Roberts Cross. Another problem is that it's anisotropic. So anisotropic just means that it works differently in different directions. So like if I have an edge like this, actually Roberts Cross does not do as well, right? So how could we change our formula? How could we change our math to actually do better in these different cases? So that's something to think about. Another problem with Roberts Cross is that it's actually really slow. At least the way I've implemented it, it's very slow. So we might want something that's faster. I do a little bit of timing here on a really big image. So this is a super high resolution image of a brick. This takes like, how long does it take? Yeah, like a minute to process that. It's pretty depressing. It's really slow. And then one other thing that will become very important, perhaps in your programming challenge, is that Roberts Cross doesn't tell you anything about the direction of an edge, right? So if I look at, let's go back to like where we computed Roberts Cross. Okay, yeah. It just gives you like a high value, right? It just gives you like just a single value for every pixel, right? It might be nice to know if an edge is going left to right or up to down. It might be helpful to know, right? That might help you make some decisions. Because when you're doing your programming challenge, maybe you say, oh, okay, I've got a straight line here, but then it changes direction, right? Or something like that. Or you could look at the distribution of directions, right? So yeah, how would you compute the direction of the edge, right? And I see a great question from Hernan. He says, what would direction look like? It's a great question. We're going to visualize it next lecture, actually, I believe. So you can look at the next lecture notes if you want. But I do encourage yourself, go for a walk, do whatever you can do in COVID to get out of your apartment or your room or wherever. And just think about computer vision a little bit, right? How would you use some math to find the direction of an edge, right? So start thinking about those things. So that's the end of class. Thanks for your time today, everyone. Hopefully you enjoyed today's lecture. I think it went a lot better than last time. We'll see you on Tuesday. Start working on your project groups and start working on the programming challenge. And that's it. Have a good rest of your week.